Hello and welcome to a new episode of the Culturico podcast. I'm Pablo Sanchez, and today we are going to be talking about the importance of mathematics in modern society. I'm a molecular biologist, so for today's show, I'm glad to be joined by Kevin Knudson, professor and chair of the Department of Mathematics of the University of Florida. Welcome to the show, Kevin.
Thanks, Pablo. It's great to be here.
Yeah, it's a pleasure to have you here today, Kevin.
The aim of Culturico's podcasts is to provide the listener with an artistic, yet realistic mosaic of human pictures. Macroscopic events of our society result from a complex combination of individual dreams and ambitions. We provide stories that have humans as their core element, from macro stories about our multifarious culture, including politics, society, and science, to micro stories of individuals' hopes, struggles, and change. Our stories are told by people with their own life experiences, beliefs, and reflections of past and present events. We therefore provide a multifaceted image of our world, observed and understood from different perspectives.
So for our listeners, a brief introduction. Kevin Knudson is a prolific mathematician. In addition to his teaching and research in the University of Florida, he writes a blog, has written several books and articles in Forbes and The Conversation, and also has a podcast of his own. It's called My Favorite Theorem, which he records with Evelyn Lamb. Allow me to go a bit off topic here for a second, as I usually love to hear how people juggle all of their life commitments, because a day has only 24 hours for all of us. So how do you manage to do all this on your time?
That's a good question. So as you mentioned, I'm chair of the department at UF, and so another chair mentioned to me the sort of joke, which is there's a lot of truth to it, which is that being chair takes about 50% of your time every other minute, and and that's been my experience too. I guess I've always been pretty good at organizing my time, and I just try to prioritize as much as I can. And the truth is, with mathematics research, what's nice about it is you can kind of do it wherever. So when I'm walking the dog, sometimes I'll be thinking about mathematics, or when I'm cooking dinner, I can think about mathematics, and I don't have to necessarily be. And that's actually usually when the best ideas come to me anyway. And then being an administrator, well, that's just grunt work that you have to grind through, and there's nothing to be done about that. And then, of course, I still like to have a life, so I really try to make time for my family as much as I can. And I don't know. I don't feel especially stressed. I don't know. I'm always amazed that. I mean, you made me sound so prolific, but I'm always amazed at other people. That how do they do all of that? It's remarkable. Some people, they publish 10 papers a year, and they're writing all these books. Like Steve Strogatz is someone who comes to mind in this way. Like how does he do all of this? And I have no idea. So I don't know. I don't really think about it much. I think that's the key, is to not really think about it very much.
Yeah. Also, in my case, I feel like I don't do enough, and then at some point you start putting on a list all the stuff you're doing, and it's like, oh wow, it really sums up to something.
That's right. I have the same experience. I feel like I'm not doing anything, and then it's over. And I go, wow, I really did a lot. That's great.
That's true. But now we are not here to talk today about productivity. There are tons of podcasts and people talking about it right now. So we'll start setting the ground with a few questions. There are a few topics I wanted to touch on. Mm-hmm. And the first one came to me, as you say, I was just walking, and sometimes the best ideas come when you're just around, you're not focused on your work and so on. And I was just thinking about mathematics and education, because that's an important topic, I think, to cover. Because I will talk from a personal experience. So when I was in primary school, I really loved mathematics. For me, it was the easiest one. It was also obvious. When I was learning, at the beginning, you start with something easy. You start just adding numbers, subtracting, and so on, basic math. And it starts to get complicated. But even when I went to the high school, it still was relatively easy to me. I didn't need to study anything. It was just like, I need to do equations. And for me, it was just very, very simple. It was moving numbers around an equal sign and from one side to the other. And it was even like pastime to me. It was something I could do in my free time, and it was very easy. But then at some point, somehow I started to get disconnected from it. And I will not blame any of my teachers, because I think they did a great job. But somehow there was like a turning point where I don't know if it's because my interest was changing slightly, or because at some point math gets to a point that it was too complicated to understand anymore. And I didn't have this training to really focus and study and see it and try to memorize some stuff. So I know I'm not only talking about myself, but I also remember all the other kids. They usually struggled a lot with math. And I've seen also in the US, the numbers show that math is one of the hardest subjects for students. So what do you think is really driving people away from math, or what do you think is making people hard to get math?
I've thought about this a lot. Well, there's a lot of answers here. One is, as you say, when you were in elementary school, you love math. And I think most children under 10 like math, because it's fun. And really, what math is about is finding patterns, and people love finding patterns. So I've always had this theory that when people, so every mathematician knows this story, right? You're at a cocktail party and you tell someone what you do, so I'm a mathematician. And the answer is almost invariably, oh, I hated math. Math was a terrible subject for me. And I've thought about this a lot. I think a couple of things happen. One is, for a lot of people, once it starts to get more abstract, and by abstract I mean algebra, once X enters the conversation, it tends to turn people off a little bit. And another thing is, students always in the US always talk about, they always ask me, will there be word problems? And that, in some sense, is less about math than it is about reading comprehension and translating reading, and the words that you're reading into the mathematics required to solve the problem. That's a whole different issue that I don't really understand, or I don't have any real insight on. And it's funny, on our podcast, a recent episode, we had a couple of people on who really interesting people, and this exact topic came up, and I mentioned my theory, and one of the other people said, no. One of our guests said, no, it's always somebody damaged them, like it was bad teaching, or someone, a teacher, and by bad teaching, maybe it's not that they weren't communicating the information correctly. It was that the teacher made them feel less than for not being able to get it immediately. And we do tend to do that. I mean, culturally in the US, it's perfectly acceptable to say that you're bad at mathematics. It's almost a badge of honor for some people. But we also, at the same time, fetishize it. It's like, well, you have to be good at math and science. You're a scientist. It's the same thing. And this goes back, 50, 60 years to the space race, where, we had to generate a lot of scientists and engineers to compete with the Soviets to get into space. A lot of our education is still driven by those ideas. And so I just sort of have a theory that nobody hates math when they're young. Something happens, and I think it's a combination of things. I really do. I think it's a combination of the getting to the abstract, and also maybe the teaching isn't as great as it could be. And then I also have another thing that I think another thing that plays into it is, and you even alluded to this, is maybe your interests change. Why do you have to love mathematics? I'm glad when people do, but I'm not offended by people who don't care for mathematics the way I do. Just as, well, I don't know, I kind of like everything, but I was going to pick some subject that I'm not particularly interested in, and maybe I don't care that much about it. Practitioners of that shouldn't be offended either. I don't think we're making it any better. My son is about to graduate college in a couple of weeks here, and he's a musician, he's a composer. But, when I watched him in high school, thinking about his Algebra 2 course was just page after page of polynomials to factor. With no context, just factor these polynomials. Why am I doing this? And I frankly couldn't give him a very good answer. And then, he got through AB calculus and he did well enough, but he doesn't remember any of it. And that's fine. Why should he? He's a composer. So this whole interest thing of, your interests change. One more thing here. So just because I'm a mathematician doesn't mean I don't struggle with it, right? So, and I'm sure you have the same experience in your own work. It's difficult.
Yeah, it is.
It's hard. You're stuck more than you're not. And so this is a really good analogy that my wife actually came up with. So my wife's an artist, and she makes books by hand, and she's really fantastic. And she loves the designing part. Like, she'll think of a new concept for a book and she'll write it and she'll do all the illustrating and all this stuff. And then it comes time to, like, she prints things with it. We have a printing press in our house, an old timey with the movable type and all that. And she cuts paper and binds everything by hand. The design part's great. But when it comes to actually producing these things, she calls that pig farming. because you got to go feed the pigs. Like if you're a pig farmer, you got to go out and feed the pigs, and you have to take care of these things. And maybe you don't feel like it sometimes. But the thing about any discipline, any academic or creative discipline or anything really, is you're drawn to the thing where, yeah, it's pig farming, but you don't mind it, right? So when you say your interests changed, yeah, your interests changed. You got more interested in biology and medicine. And so that's the pig farming you like to do. And there's nothing wrong with that. Well, yeah, there's absolutely nothing wrong with that. You know, I think everybody should farm what they want to farm. I'm happier farming mathematics.
Yeah, it's a great analogy. Yeah, I think it has a part of truth in which your topics change and your interests change. And then it's exactly that point where you say you have to go into the abstraction of mathematics. At the beginning, you're just adding and subtracting things. And that kind of makes sense for kids where you do the analogy with, I don't know if you did the same in school with the cookies. Like you have 7 cookies and then you give away 3 cookies, how many cookies you have. This a kid can relate to immediately. He doesn't want to give away any of the cookies. But as soon as you get into something more complex, I think it's when they feel the disconnection of this topic with reality, with what's this for? And the only thing people usually come up with is taxes. And nobody likes to do their taxes. If the only math or the only real life problem where you have to use some math is calculating your taxes, who wants to study that?
Well, but the thing is, that people are using math all day long without realizing it. So, for example, one time we were having our kitchen floor redone. This was 15 years ago. And we were having new tile put in. And, I was watching this man lay the tile in my kitchen. And we talked about what we were doing. And I told him I'm a mathematician. He said, oh, boy, math was tough for me. And I said, what do you think you're doing right now? And he just sort of looked at me. He's like, what do you mean? It's like, every bit of what you're doing here is mathematics. You're having to spatially lay this stuff out. Every time you pack your car to go on a trip somewhere, you're trying to get all the luggage in there. Maybe you got a lot of stuff. That's a math problem. And I think math has a PR issue. I think we could really do much better public relations in trying to get people to see that, really mathematics is really beautiful and it's everywhere around you. And it's really about patterns. And my son, when he was in preschool, the teachers were always surprised. Wow, he's really good at patterns. And I said, well, okay, fine. Well, he's a musician now. So it's sort of funny how these things sort of play out as you go. And so, he doesn't need advanced math in what he does, but it's under there. And he's a percussionist, so he can count to 4 really well, right?
Yeah, true. So in biology, we say, or at least we said when I was studying, that from all the sciences, if you rate them from purest to the most applied, you always go from math to physics. Then from physics, you usually go to chemistry and biology, and then you go to medicine. So it's step by step. And I think that's the reason, as you say, math is in everything. Because everything I do in my job, everything I do in my research has a base of math.
Sure.
Problem is, the farthest away you get from math, the less pure your calculation is. The more you have to assume and the more you have to rely on things like statistics, where you're not talking about pure numbers. A is not equal to 2b anymore, but A is equal to 2b plus this number that we don't know exactly what it is, plus this other thing that we really don't know if it's exactly a number, and we don't even know if we can quantify it.
Right. But in some sense, that's more interesting, right? I mean, so things with exact answers are, they're not dull, of course, they're really fascinating, but that's a separate thing. It's sort of, the more experimental side of science is where you're messing around with the numbers and you don't exactly know where they are. You don't exactly know what your model is. That's really hard.
Yeah.
Yeah. Some pure mathematicians sort of, have a snide attitude about applied mathematics, which is just nonsense to me because applied math is really challenging.
Yeah, that's true. Now I wanted to touch on a topic because it's going in the direction we are going to drive this podcast today. And it's that people don't really realize about it. And if you ask someone what they want to do and they want to go to business school, then you say, well, there's math there. And they want to become economists. There is a lot of math there. They even want to become a politician. Well, I'm sorry to say there is a lot of math also there. Maybe he's not going to be the person that has to work with the math, but there's going to be a lot of math involved. And we're going to go to that topic later. And for that, I wanted to touch a few things on how we can apply math to problems in society, or how do we analyze problems in society using math. And I wanted to start with the things you do. So you're researching in computational topology. Just by that name, it's really hard to relate what exactly this is doing. So can you really explain what it is and how can you apply it in real life problem or even in your research and your problems you try to solve?
Sure. So let's see. What's the quick explanation of what computational topology and topological data analysis is? That data has shape. That's the mantra. So, perhaps in secondary school, people have seen examples of you have a scattering of points in the plane. They represent some kind of data set, some measurements, who knows. And the first thing you try to do is draw the best fitting line through that. And that's an example of linear regression. It's well understood. It's not too difficult to do. It's a standard linear algebra problem. And there are, of course, higher dimensional versions of this. You have just points floating in space. No matter how many dimensions, you can sort of try to find the best lower dimensional plane that fits it. So great. And again, this is sort of well defined. But here's an example. Imagine you look at this cloud of points that happens to sit in the plane. And instead of kind of looking like a line, maybe they look more like a circle, right? Or imagine that you just sort of, there was a circle sitting there and you tried to grab points off of it, and you were sort of imprecise about it, but, they roughly look like a circle. Okay. Well, now, if you try to fit a line to that, you're going to get a terrible answer because lines don't model circles very well. So what might you do? Well, if you think it's a circle, how do you prove that it's a circle? More, and even sort of more to the point, how do you get a computer to tell you that it's a circle? Right? In other words, you want to take the human eyes out of this, because to abstract this further, I know we were talking maybe about abstraction being the problem, but imagine now that this circle, instead of sitting in the plane where you can see it, was really a circle that lived in 234 dimensions. It's still a circle, right? You can still have a one-dimensional circle sitting inside some higher dimensional object like that. You can't see it anymore because you can't see that many dimensions. But you still know you have these points. You're just handed a list of points, and can you decide if this thing really came from a circle or not? So that sort of creates all kinds of interesting questions. But what topology is good for is for taking spaces, geometric objects, and associating to them various other, usually algebraic type of objects, or sometimes just a number, that tell you something about the object. So for a circle, the relevant thing it's called the first Betty number, and I won't tell you what it is, but it basically, what that number measures, it's an integer. It tells you how many circles you have in your object. So for a circle, for just one circle, the answer is 1. And so getting a machine to spit out 1 from this data point, from this cloud of data points, is sort of what computational topology is about. And the standard technique is something called persistent homology. And the idea is you imagine around each one of these points, you start with a little ball, and when the balls are really small, they won't touch. But as you let the balls grow, they'll start to join together. And you can imagine, again, thinking about imagining this in 2 dimensions, you let these little disks, grow, and then eventually they'll all start to touch, and you can see a sort of a fat circle sitting there. And algebraic topology then has the sort of computational techniques we have would tell us then that, this Betty number I mentioned is 1 for certain values of these radii. So that's sort of the meant to be short answer of what computational topology and TDA is about. And of course, it's it's a lot of other new directions you can take that, but that's the idea. So data has shape. This has found lots of interesting applications in medicine and neuroscience. And there was this one sort of famous data set about diabetes that people thought was pretty well understood, but anyway, they applied some TDA to it, and they essentially discovered that there's kind of a new subtype of diabetes with this information. It's been really good for like in cancer research, proving if you think a drug is 85% effective, well, okay, that's an interesting question, but wouldn't it be better to know that it's 100% effective on 85% of the population? So TDA is also sometimes good for figuring out things like that.
Yeah. I wanted to know what exactly drove you into this when you started studying and you decided you wanted to go into this field. When exactly did that happen and how?
So, my history with mathematics goes way back. I was always just sort of good at it in school, but, no one in my family had ever gone to college. So, it was sort of this, when I was about 14, I thought, you know what, I'm going to go to college, but not only that, I'm going to go to graduate school, get my PhD in math and be a math professor. And then I did it. I mean, it was, sort of the audacity of that. I just thought, oh, this is what I'm going to do. And, it's funny. So, I started my career in mathematics in a different area, actually. I mean, I've always been a topologist, but I used to work in something called homology of linear groups and algebraic K-theory. And I did that for probably 10 years or so. And weirdly, there are a lot of K-theorists who end up doing computational topology too. I'm not sure why that is. I think K-theory is hard. And, you learn all this topology and then you start to just think, oh, here's this interesting new thing that's coming along. And so, I had already gotten tenure. I had the luxury of having tenure, which is nice when you decide you're going to change research directions. And so I went to a workshop at the Institute for Mathematics and its Applications, and this has been, 15, 16 years ago now. And that's when I made this switch into computational topology. It's been really, an interesting path for me because I'd never really thought about any applied math before. And I guess to be completely honest, I mean, I'm still on the theoretical side of computational topology. I mean, you might think it's all the computer work. I can't code my way out of a wet paper bag. I mean, I'm terrible, but I can certainly think about the theory, and that's so. What I like about TDA is there are a lot of interesting fundamental foundational questions that can be asked where I could put my sort of topological skill set to use, and then to see that there are applications coming out of it on the other end. I mean, that's sort of really what drove me to it. Plus, it's a good group of people. When a scientific community is sort of welcoming and just full of interesting, nice people, it's easier to gravitate into that too. And I would say TDA is one of the better ones.
And you say there are applications coming out of your theory. Can you share a specific example or something that they're using your theory to apply to some?
So I guess my most cited paper is this joint paper I wrote with Henry King and Neja Muramwar. And it's about discrete Morse theory, actually, which is, again, we don't need to get into the details, but Morse theory in the classical case is sort of a way of studying how critical points of a function affect the topology of a manifold. So the simplest example is imagine taking a donut and you dunk it into a cup of coffee. And as it's starting to sink below the surface, at first it's just a little bowl shape that's below the surface, and that's not very interesting. But when you get to the bottom of the hole, suddenly something changes. Now you've got a cylinder, essentially. So the topology changed when you got past that point. Discrete Morse theory is a way of doing this, on objects that you might put into a computer instead of smooth objects. And so what Henry and Neja and I did was we sort of came up with, I guess it's really sort of the first algorithm for taking what you might think of as, imagine you have some shape and you sampled, and you have a function on that shape, but you don't know the whole function. You just sampled it at some points. Then you might begin to ask, what can you say something about kind of like the Morse theory, whatever that means, of this function? In other words, can you sort of interpolate this function in a way that makes sense with respect to the topology? And so we came up with a good algorithm for doing that. And so, specific application, I don't know, discrete Morse theory gets used all over the place in TDA to reduce other calculations. I know that paper's been cited a lot, but I can't think of any, any really exciting examples off the top of my head where it's been used. My own, I mean, I like to mess around with things. I've sort of played with like speech signals. I was trying to figure out a way to get like a speech recognition algorithm using TDA, but that didn't work out so well. I mean, you just play around a little bit. Not everything works.
That reminded me to the joke of mathematicians try to measure the weight of a cow, and then they started saying, "Imagine the cow is spheric." So you just reduce the cow to a simplest shape that you could measure, and then it's much easier to do it.
Well, but in some sense, why not, right? I mean, imagine it is spherical.
Yeah.
Why not? I mean, because topologically it may as well be. This is what. So yeah, I mean, now geometrically it isn't, right? This is the difference between topology and geometry. So to a topologist, a tetrahedron, a cube, they're the same as a sphere, because you could imagine if the surface is made of some stretchy material and you stuck a straw in it and just blew out, you'd get a sphere, right? But a geometer, of course, would go, no, these things are completely different objects. And that's true, geometrically. So that is sort of the difference. But if you're just trying to compute some simple invariance, yeah, just assume it's a sphere. Why not?
Well, that's really, really interesting, to be honest. And now I wanted to go into other topics, but something they probably can relate to. Especially, I wanted to start with how are we applying nowadays math in everyday decisions and in society. And I wanted to start with a topic that it's relatively close to us right now, because as we said before, most of everyday decision and everything we do, it's driven in one sense or another by mathematics. And in some cases, as the renovations on your kitchen can be very subtle, it might be just a bit of geometry, taking some measurements and calculating how many tiles they have to place on the floor. Or it can be way more obvious. But basically, most of the decisions that we take, they have something calculated, some component that we have to calculate. Then now I wanted to touch on one of these topics that has been driven by numbers for over a year, and that has been the current pandemic. So I wanted to discuss about the political choices that have been made. I don't want to go into if these choices have been right or wrong.
Yeah, that's probably wise.
Yeah. But I wanted to touch the point on how these decisions were made and which numbers they had to count on and which kind of models they had to set. And for that, for example, talking about the pandemic, I can say from my experience, what I've been reading this past year and what I can understand from my field, the main numbers that I focused on were the number of infected people, the countries that were affected by it, and the percentages of people that were going into ICUs or were having complications, and the number of deaths, the saturation of the hospitals, and so on. And I think, thinking from a human side, that's the first number that comes into our mind. But there have been many other things to take into consideration every time one of our politicians had to make a choice and their team were coming to him with different numbers. There is not only the people getting sick, but there is also the consequences of their choices. A lockdown like we had in the US and like many other countries around the world has way more consequences than just reducing the spread of the disease, which is the main point of doing a lockdown, is reducing the spread of this disease. So we don't saturate hospitals, we don't run out of resources, and then we don't have mass deaths in a country. But locking down also means halting the economy of a country. It means stopping life as we know it and stopping everything we do, which will have way more consequences than just reducing the spread of the disease. So experts have to value the both sides of the coin and thinking the benefits of doing this lockdown, for how long are they doing this lockdown, and the consequences it will have later on in many other areas like job losses and people losing all support they have, the lack of income. People need to pay for food. So if you extend the lockdown, for example, for too long, then people at some point and a country at some point will run out of money, and the consequences will be much worse than just letting people go back to work. So do you know, or could you maybe comment on how are these numbers calculated? Which kind of modeling they have to do? Because it's not, at that point, it's not only epidemiologists and biology. We had to move a lot of numbers on a table and we have to assume a lot of things. And what kind of modeling, what kind of assumptions, and what kind of numbers are used in a situation as extreme as this one?
Yeah. So I'm not an epidemiologist, nor am I an economist. But so from the epidemiological point of view, I mean, as you mentioned, there was a lot of data, and as you say, sort of case numbers, hospitalizations, things like that. And so the basic, the number that's that is always getting thrown around is R naught, right? R naught is the basic, the sort of basic measure of how contagious something is, right? So it's sort of the average number of people that an infected person will infect. And so you want that to be less than 1. If R naught is less than 1, then eventually the thing dies out. What's interesting about, this is, you learn about these things in sort of your first in university, in sort of a first differential equations course, where you learn about the logistic model and things like that. And those models are interesting. They have a lot of assumptions. So there's this old saying that, all mathematical models are wrong, but some of them are useful. And so and this is where I sort of sympathize with public health officials, is that they're dealing with data, but the models are imperfect. There's no way to model this exactly. There's so many confounding factors. There's, okay, fine. So New York City was terrible at first. They locked down. They eventually got it under control, but then, it started spreading elsewhere. And then the question is, well, should you lock down? So in Florida, our governor tried to have a more open approach. We can argue about whether or not it worked or not. I mean, Florida's not great right now, but it hasn't ever been as bad here as it was at its worst elsewhere. So, the models are what they are. They're sort of, we have some standard models, and epidemiologists are really they're smart people. They're good at this. They know how to take the data. They know how to account for a lot of these sort of non-homogeneity, right? I mean, it's much different to try to deal with this in a rural environment as opposed to an urban environment. Should you target lockdowns? All these things. So I actually feel like the epidemiological folks, let's take partisanship out of it. I think they did the best they could, and I think they were giving sound advice. Whether the politicians took it or not, or wanted to accept it, is a different story. But as far as and then as far as the economy goes, I don't know. I guess I'm more of a socialist. Money is a construct. So we could have locked down. We could have paid people to stay home, right? Now, of course, you can't pay everybody to stay home because, as you say, people have to eat, right? Grocery stores have to function, and, farms still have to produce food and things like that. So there was no way to eliminate risk for everybody. But I think there were ways to, I think lockdowns were sort of generally, clearly they worked to some extent. Things were really pretty bad in the United States, but I guess they could have been worse. They certainly could have been worse, as we're sort of seeing now in India, where, but again, sort of a much different thing, right? India, 3 times the population of the United States in a smaller area, they're going to have different sorts of issues. So, what calculations do politicians make? That's a good question. I think things got way too political.
Yeah.
Whether you agree with those politics or not, I'm more troubled by sort of how scientific expertise got pushed aside when it was not lining up with the political views of certain people, and that's disappointing. So, yeah, this is a hard question, Pablo. I don't, not knowing. But the economic models that I sort of read were like, well, yeah, people are going to lose some things, but we can pay them. The federal government can essentially borrow the money from itself and pay it back later, and send people a check so they can stay home. And maybe the short, if you do just dump a bunch of money into it on the front end, it tends to come back to you later through taxes and increase productivity down the line. So
yeah. I think it's been a really hard situation, and that's maybe taking it to the extreme, because we were basically working day to day with new numbers. And I remember during the lockdown, we had an online talk by Anthony Fauci at Stanford. And then when they asked him about what he thinks about the pandemic, was one of the first questions. And then he said that basically, like, every epidemiologist's biggest nightmare just came to truth. It came to fruition. Like, you have a virus that it's very, very infectious, but also very deadly. Mm-hmm. And it's easy to spread, and it's very easy to kill people. So what do you do in this situation? You have to act very fast. And we know that in politics, things are not usually done the fastest they could.
Right.
And there are many things. And I think the problem is that, as you said, we are, as a society, we are very good at making everything a partisan issue. And as soon as something becomes a partisan issue, then we put aside every number, every calculation, or every model that could be used. Because now it's not important how much we can do about the economy and how much we can do about people, but it's more important what can we do about, or what can politicians do about themselves. Also, another example here in California, we had a quite strict lockdown at the beginning, and it's been harsh compared to other states. Like the mandate about masks and gatherings and so on has been maintained for very long. And as soon as there is a bit of more infection rates outside, then immediately the restaurants and public places were closed and shut down. And this has been very bad for the view of our politicians. Like the popularity of Newsom dropped a lot when he locked California the second time. So in their case, I think they don't only need to look at the numbers of the pandemic, which are, by now, we have a pretty good idea of how this virus is spreading, even though every day we come with something new variant, and suddenly it's faster or slower. But we got really good at reading these numbers and knowing what's going to happen if we don't lock down or if we just let it go. And at handling this, we got good. But then it comes the second issue, which is taking this decision and locking down again. What's the political cost of this?
Right.
And whether politicians are ready or not to take this toll and maybe risk losing their next election is what in the end is going to drive a lot of these decisions. And then I think that's the point where you forget about all the math, all the statistics, and all the sound advice that you could get, and then you start thinking about something more personal.
Yeah. Well, and of course, California had a different issue, right? I mean, so, and even California isn't homogeneous, right? So, the coast, I mean, so you live in the Bay Area, it's extremely crowded, right? But you go over the mountains and nobody's out there. So, I mean, so do you lock down a whole state? Do you lock down? I mean, and this is where, targeted local lockdown. So for a while there, Los Angeles was essentially the worst place in the United States for it. So fine, you needed to lock down in Los Angeles, but did you need to lock down in Fresno? I don't know, right? So this sort of gets to this idea of scale, right? I mean, I don't actually believe in one size fits all solutions. I think, there are scales to things, and sort of computational topology is good at looking at multi-scales, not at this problem, but just, solutions that work at one scale won't necessarily work at another. And I think it's a challenge for a governor of a large state like California to deal with that, as opposed to, some place like, North Dakota, where even the most densely populated places are nothing at all like Los Angeles, So I guess the point is, politics anymore has thrown nuance out the window, and there's always looking for a simple solution, and this problem did not have a simple solution. So here we are.
And then if you abstract the model even more and you say like a place like Los Angeles, which had a really, really bad pandemic there, and then you consider relatively close, you have Phoenix and you have Colorado and so on. And they didn't have such a big problem. But then when you abstract people into dots and numbers, these dots are not fixed in a point of the plane. If you just draw them on a plane, they will move around. And
That's right.
you need to consider also this equation into place, where even if Phoenix is doing fine, people from LA are going to move around. And not even people, but also food. The food from California has to reach Phoenix because they cannot grow vegetables there. And the lettuce has to arrive from California, and everything extends. And the scale of, even though we have to use local decisions according to the numbers in our area, we also have to put this into the equation. And we also have to calculate this into it. And it's been really hard to calculate. I don't think we could say there is an answer to that we could obtain from numbers only.
No. If only.
If only, right? That would have been much easier.
Yeah. I mean, I do think people have expertise that could have been listened to better. But there is also, the thing is, we can't run this experiment again, nor do we want to. But, it's It's always these things of, well, we could have done it differently. Yeah, we could have done it differently. We might have gotten better outcomes, but we won't know that.
It's easy to look backward
That's right.
and say, oh, that was a big mistake. But at the point, you really didn't know the outcome. And as you say, we cannot run the experiment again. If something doesn't work in the lab, then okay, we just restart and we do it again. But when something doesn't work in real life and in situations like that, then you get the problems. And it's really easy to look at the outcome and say, oh, that was a really bad decision. But you have just a limited view at the beginning. Yeah, and I wanted to touch on another topic regarding also politics. And it's something interesting because it can be measured afterwards. So there are many other decisions that politicians take. And in that case, they look at the numbers much more. And the one I want to talk about is gerrymandering.
Yeah.
You're probably very aware of this topic.
I have written some stuff about it, but no, go ahead. I think I cut you off.
Yeah, maybe I wanted to introduce a bit of history here about the topic because the people not living in the US might not be aware of what gerrymandering means.
Okay.
So the term was coined after the Massachusetts governor, Elbridge Gerry, which in 1812, he planned a district redistribution in the state. That basically is changing the boundaries of the political districts. And he created a new region that was clearly designed to favor his party in future elections. And this was made very clear because if you look at the map and the new district, this new district has a very weird shape and it was looking like a salamander, right? And then there was a satirical cartoon of the new district in the Boston Gazette. And they showed this cartoon and they just coined the word by mixing the words Jerry and salamander. They just came up with the word gerrymander. And since then, every time there has been redistribution of boundaries and changes in the state to alter the outcome of the votes, then this is the term that it's being used, gerrymandering. And that's because in the US, the election system is an all or nothing. So all the seats on a certain district are going to go to just one representative.
Right.
And then all the votes for any other representative are going to be lost. So it's very easy to move a region, let's say an example, like a big Republican region. Then they can change the shape of their district. So they include another city that it's mostly Democratic, and it was giving votes to another district. But now it's coming into this big Republican district where these votes are in the end going to be wasted because they are not going to vote for anyone. Mm-hmm. And also the other way around. And it's been done by all sides and
sure.
in many cases. So this way, politicians can really cancel regions of the map and they can take advantage of their legislation to benefit their party. And this was very clear in the case of Massachusetts, and there have been a few others in history that if you see some districts, you clearly see they shape these districts to try to alter the votes. But even in the ones that are not clearly seen, they cannot really escape the numbers. And I've been reading a bit about that, and I know you know a bit also about it.
Mm-hmm.
And I wanted to know what can be done. How can mathematicians and political scientists find out when politicians are gerrymandering?
Yeah. Well, so it's, as you say, it's often obvious, but sometimes it's more subtle than that. So there's a lot to say here. Boy, there's so much going on here. So this is, okay. Now, I do love talking about this. It's really, because it is sort of fascinating. The thing about the American political system is that nothing is guaranteed, you know. So the Constitution was written a certain way. And then, you know, enterprising politicians have tried to figure out ways around it ever since. So, for example, I live in Florida, very large state. We have 27 representatives in Congress, in the U.S. House of Representatives. And so you might ask, how many of those are Democrats and how many are Republicans? So in the last election, the 2020 election, it worked out that 27, 14 of them are Republican, 13 are Democrat. And if you look at the statewide, if you just sort of count up all the votes in the state, the Republicans had more votes statewide, but not by very much. And so 14 to 13 would sort of look fair If you didn't think about it any more deeply than that, it would look more fair. You're like, well, that's about right. Okay. By contrast, so I grew up in North Carolina, so I still pay attention to North Carolina politics. And North Carolina's congressional, and I'll say more about Florida in a minute, but North Carolina's congressional map is one of the most gerrymandered in the country. And several years ago, Jonathan Mattingly at Duke really kick-started a lot of this analysis. And sort of at the same time, Moon Duchin at Tufts got really interested in this too. So in North Carolina, in one election, I forget which one, 2014 maybe, statewide, if you added up all the votes from the House of Representatives, the Democratic candidates got about 51% of the vote, and Republicans got about 49%. But of the 13 congressional districts, 9 of them were Republican, and only 4 were Democrats. So even though the Democrats got more votes statewide, they only got 4 seats in Congress. And you might say, so now, okay, Americans like to think that we value fair play. You might say, look, that's not fair. There's no way that's fair. And yeah, I don't think it's fair. But, there's nothing that prevents the politicians from drawing the maps the way that they're drawn. The Constitution gives that authority to the state legislatures. The state legislature in North Carolina is heavily Republican, again, partly because they won the right election. They won the election in 2010. That then allowed them to redraw the lines to their advantage in 2012, and then further solidified their supermajority later as it went on. And they just keep doing this. The thing is, so you might say this isn't proportional, right? The Democrats got more votes, but they, if it had been, 7 Republican, 6 Democrat, even though the Democrats took more votes, you might go, well, that's kind of all right. You could see how that might happen. But 9-4 seemed a bit much. The thing is, the Constitution does not guarantee, there's nothing in there that says that you have to have proportional representation, right? So there's 2 things going on. We say, okay, well, look, proportionally, the Democrats should have gotten more seats. That's not one of the conditions. It's not one of the rules. It doesn't have to be that way. And the Supreme Court has repeatedly reaffirmed that. There is no guarantee of proportional representation. So that's where a lot of the issues are coming up. It's like, this isn't fair. It's not fair in the sense that it feels unfair, but it's not violating any rules as they're written. Now,
yeah, it's not unconstitutional.
It's not unconstitutional. And in fact, pretty recently, in the last couple of years, Wisconsin is another example of a state that is heavily gerrymandered in its state legislative districts. I mean, it's obscene. And a case got to the Supreme Court about it, in which Chief Justice Roberts essentially said, just shrugged his shoulders and said, the Supreme Court can't do anything about political gerrymandering. It's disappointing. Again, I mean, the argument is somehow, well, it's up to voters to fix this. But when you bake in such a structural advantage for one party, it's difficult for the other party to overcome this. It's not impossible, but it's difficult. So back to Florida, our state legislature is similarly gerrymandered, but the districts look reasonable. You mentioned the shape of this district. So I'll even talk about my own district for the State House of Representatives in Florida. It consists of 3 counties, 3 entire counties. It's not even cut. The counties aren't cut in any pieces or anything. So you say, well, this seems like a reasonable thing to do. Gainesville, being home to the University of Florida, as you might imagine, is a fairly liberal town. And in our most recent state legislative election for the state house, the incumbent was a Republican named Chuck Clemens. And the challenger was a Democrat, a physician here in town named Kaiser Enneking. And she got way more votes in our county, like about 57% of the vote. The other 2 counties are much smaller. They're rural counties. I mean, not like our county isn't. It's mostly rural too, but I mean, it's very rural, these other 2 counties. No real significant towns in them. And so in those 2 counties, each county accounted for maybe fewer than 10,000 votes in each county. But the Republican candidate got almost all of them, like 90% of the vote in those 2 counties. And so even though the Democrat won convincingly in our county, and the other 2 counties were much smaller, it was just enough for the Republican to win the whole thing. Now, there's nothing illegal or unconstitutional about this, except that Gainesville, which is a pretty liberal town and is the major population center among all of this, is not getting the representation that it voted for. Okay, so that's when people really start to get frustrated by the whole system. And so I had a student a couple of years ago, and we ran an analysis on the Florida legislature, and yeah, it's gerrymandered. Even though the districts look okay, and the Republicans statewide do have more. They do win more votes statewide. Florida is actually a rather rural state, except outside of Miami and Tampa and Orlando and Jacksonville. So for the Republicans to have the majority is not surprising, but they don't have that many more votes. In other words, it shouldn't be a supermajority like they have. And it's a supermajority because of how they've drawn the district lines. And so this is where we are. The math we used to do this was really interesting, and I didn't develop any of this. I just think it's cool. So Jonathan Mattingly started this, and also Munduchin. It's called MCMC. It's Markov chain Monte Carlo methods. So the idea is essentially you take the data from a previous election, and you then so those are given, right? So the number of votes at each precinct. Voting precincts don't change. The way you draw districts is you gather precincts together into a district. Mm-hmm. So, but the precincts never change. They're just sort of fixed. And so now you imagine, well, what if you combine these precincts in different ways to get different districts? And so you sort of run these simulations, and you sort of start at one, and there, of course, there's all kinds of rules that come into play with how you can actually draw valid districting plans. You have to take into account things like the Voting Rights Act of 1965. Things have to be contiguous. You have to, there are rules. The population has to be roughly, and by roughly, I mean almost exactly the same from district to district. You have to balance all of these things. But you can imagine, but there are, of course, an enormous number of valid districting plans that you might draw. And so you draw one, and you check the results on it. And what MCMC does, though, is it sort of starts at a valid plan, and it takes kind of a random walk through this space of possible valid plans, and you just check what happens at each of them. And then you sort of then get statistics on what you would expect to happen. And, when you do this, so Jonathan Mattingly did it for North Carolina with one of his students, and figured out that really for that it should have been something like 7 Democrat and 6 Republican instead of 9 Republican and 4 Democrat. And here in Florida, instead of it being what it is, it should be much closer. The Republicans should still have a majority, but it shouldn't be an enormous majority. And so there's all this really interesting mathematics around this. So that's one thing, the MCMC process. There's another thing called efficiency gap. That's what was actually at issue in that Supreme Court case involving Wisconsin, which, as you were alluding to earlier, votes get wasted. And so you might try to, choose a districting plan that sort of optimizes for that. Mm-hmm. In other words, to minimize the number of votes that you waste. That turns out to not necessarily guarantee you anything either. You mentioned the original 1812 Elbridge Gerry with his weird salamander-shaped district, which, by the way, that eventually backfired for them, but it worked for a little while. But as most things do, you might think, well, you can always detect by shape, and there are some weird-looking congressional districts. North Carolina being one of them. There was this sort of very famous one, NC-13, which ran the length of an interstate highway all the way from Durham to Charlotte. This is 150 miles down a highway, and that's basically all it was. And a little finger that went over to my hometown in Winston-Salem.
Yeah, something to the northwest.
Yeah. So that northwest corner, it brought in. It's a minority district, so the representative for that district is African American, and it even touches my hometown, but the more African American part of my hometown. It was deliberately designed to. This is another strategy. It's called packing and cracking, where you pack all your opposing voters in another district. You essentially sacrifice 1 or 2 seats, mm-hmm. and then take all the rest, which is what they were doing in North Carolina. And again, you can argue about whether or not that's fair, but it is a strategy. But there's a few years ago, someone proved this is a really interesting paper. You can find it on the archive somewhere. It's kind of there's Arrow's impossibility theorem about voting systems, where basically the only thing that satisfies sort of the minimal things you would want is a dictatorship by one person. There's kind of an impossibility theorem for drawing districts. If you want to insist on compactness, which you have to, so they have to be relatively compact, and you want to sort of minimize the efficiency gap or something, then you're going to end up with weirdly drawn shapes. You're kind of forced into getting these shapes that look really weird. Some of these weird looking shapes are completely constitutional. There's one in Chicago that what's called the earmuffs. It's sort of a U-shaped thing, And on one end, it's really literally just a highway wide to make it contiguous. But it's valid because a judge ordered such a district to be drawn. It's a majority Hispanic district. So it's complicated. Mathematicians can analyze these data. We've got really good techniques now. The Moon Duchin's group at Tufts has really done a lot of, it's the metric geometry and gerrymandering group. They've got really cool software out there that you can use to play around with these things. And you can just do the analysis for yourself to see, is your state, well, it's not as easy as all that. You have to, shape files turn out to be the problem. But really challenging mathematical problem. Of course, the political scientists say that this is a political problem. In other words, mathematicians have nothing to say, which I don't really believe. But I know some political scientists who do think we should just butt out and not say anything. But no, we have something to say. But it's true. In the end, it's a political problem.
Yeah.
Right.
But I guess politicians and legislators, they run these simulations too to choose how they change the districts. They just don't guess. They probably use some numbers and they run this software, these plugins to try to find the best distribution.
That's right. They don't do the MCMC. They might do the MCMC.
They might do it now.
But they were very good. They'd gotten very good at sort of these like block level drawing of these districts to really if you put this neighborhood in with somebody, you'll get a different outcome. They got very good at that. It's very cynical. It's just such a cynical manipulation of things by which you're just trying to consolidate your power by choosing your voters.
Yeah.
And that's so to me, that's what drives me crazy about it.
Yeah.
I don't think it's fair that anybody does it. I have my political persuasion, but I don't think anybody should be doing this. Mm-hmm. It's sort of fundamentally unfair.
Yeah. And from the way you talk about it, I guess there is nothing really that can be done. Even if we find out there's been gerrymandering, there is no way we can block it, right? Even if we run the models and we find out it's clear that they shape this district just to, as you say, cancel voters. Is there anything else we can do apart from just publishing or writing on a journal or in the newspaper?
No, one has to apply pressure to politicians. So some states have moved towards nonpartisan districting commissions instead of having the legislature draw. If you think about it, why should it be that every 10 years, the party that happens to be in control of the legislature gets to draw these lines? Now, we want to believe that everybody's fair-minded, right? But the last decade has proven that that's not true. So, because of how things have gotten. So, if you have an independent commission to do this, you tend to end up with better results because they're just going to try to equitably draw things, usually leaning more towards a bit more like proportional representation. California is a good example. So California has this nonpartisan districting commission. And, California actually just lost a seat in the House, but had 54, right? In the current Congress, California has 54 representatives, I think, many of whom are Republican. But if the California legislature, which is heavily controlled by the Democrats, wanted to, I think it's possible to partition California in such a way that the Republicans wouldn't have any representation in Congress. I actually think it's possible. Maybe it might be trickier around Orange County, but I think it's and Eastern California is actually pretty conservative, right? But I still think if you sort of drew the districts kind of across the state, you could make it in such a way that the Republicans, but that wouldn't be fair, right? Because then all those people who live in do all the farming out in the central and eastern part of California, which might be more conservative, might tend to vote more Republican, would have no representation in Congress. But they do because, Kevin McCarthy, for example, is, from California. So, it's fair. We actually want the representation to be somewhat balanced. And when one side does it to the detriment of the other to an extreme, it's just not fair. It's just, it just sort of violates our fundamental ideas of fairness. But, what can mathematicians do? We can point it out. This is where we have to put on our citizen hats and go, wait a minute, I don't like this. This this is clearly not right.
Yeah, I was being very dramatic saying that we cannot really do anything, because I think raising awareness about the fact that this is happening is already a lot. And
Sure.
And that's what we can do. We can say it. We can show it with data. We can calculate and show how they are canceling votes, and we can write about it. And I think in the end, this is what's helping people realize that might be an issue. And when it becomes an issue big enough, we'll ask for a change, if possible.
Let's see.
At least we have to try our best.
That's right. I mean, next year will be interesting, right? Because we got the census figures now, and next year legislatures will redraw the lines. Florida gained a seat in Congress. What's going to happen there? I don't know.
We'll see if we'll keep seeing the same practice or there'll be a change.
Yeah.
Because I guess this legislation was done to try to redraw districts in a way that they include the representative population of the area. So if cities change their shape and also people move from one place to another, you'll want to redraw in a way the state that it keeps including the same representation. But then this is just basically distorted in a way that is not representation of what was the idea of the concept at the beginning, and
right,
and then just used for the benefit of a single person, a single party.
Right.
So it will be interesting to see do you think it is possible to in the near future change the law in a way that this movement of boundaries, this change of boundaries, could be only analyzed in a way that there is no human interaction with that. But we have models that are good enough, I think, to find out when a district has been gerrymandered. So do you think we could go into these models just to change if, let's say, in 20, 30 years, the population of a district change? Then we have a model that says the boundaries in this district have to be changed. So there won't be any human interaction there. There is no way politicians could change it. Do you think it's possible to include this in a legislation in the future? Or that's a very idealistic view of politics?
Yeah, I'm way too cynical to think that'll ever happen. You can't completely automate it. I mean, because there are factors that you have to take into account. So political gerrymandering, the Supreme Court has decided it can't do anything about. Racial gerrymandering is illegal.
Mm-hmm.
So that violates various federal laws. So you can't just put it on autopilot. But I think autopilot is not bad for a first approximation.
Yeah.
And there's sort of this straight line algorithm. And the idea is you basically, you're going to cut because you see all these weird boundaries, on districts. And what you can do instead is just try to get polygonal regions. And you just kind of, you do it algorithmically by, so let's assume you have an even number of seats just because it's kind of easier. Well, it doesn't actually matter. Assume you get an odd number unless you have a power of 2. But so you start with however many, let's assume you have an even number to start with.
Mm-hmm.
So you just find the line that isn't vertical. You just find the line that chops the state into 2 pieces of equal population, right? Because you have this population business. You have to make the districts of the same size. Okay, now you've got 2 smaller states. Iterate this process. Okay, and then what you end up with is when you have an odd number, you have to of things left to do. You have to choose a certain thing or whatever. You can kind of imagine how this would go. What you end up with is a bunch of polygonal, like straight line boundaries for your regions, and you end up with at least in terms of population, something that is even. And then it was drawn without any sort of bias with respect to anything. It was just, where the people happen to live. You just,
mm-hmm.
But then you start to go, okay, but was this really fair? And, it's fair in one sense, but in another sense, our laws are also written in such a way that, so-called communities of interest are supposed to be kept together. So maybe in a particular state, this line, one of these lines you drew, cuts a Native American reservation in half, or into pieces. Thereby, you've chopped this community of interest apart. So that's no good. You can't do that.
Yeah.
There are all sorts of complicating things that a strict algorithmic approach.
But you can even include that into the algorithm, right? There is a way that you can factor in that.
you can, but then it suddenly becomes a lot more complicated, right?
Yeah.
So I mean, so and as we were saying earlier, everybody wants a simple solution to everything, right? So the simple solution is you just draw these polygonal lines and that's it.
Yeah.
Okay, but now that actually turns out to not be the way to go. And as you say, you can correct for these things. I think it's possible to get a better system than what we have, but I think the first step is to move to sort of nonpartisan districting commissions where, a group of concerned citizens actually gets to draw the lines. I think that's sort of a better way to go.
Yeah, that would be great. Not only in drawing the lines, but in many other choices. Would be nice that the group of citizens would be able to do these things without any kind of political affiliation or any kind of partisan consideration in mind.
Right.
No, that's really, really interesting. I could be talking about it for hours because it's a topic that it's especially fascinating for me because I'm relatively new in US politics. I've been here for 4 years now.
Mm-hmm.
And then even though we, from Spain, where I'm from, we used to follow the US election because it's an event that is important for the whole world.
Sure.
We were not clear about how it works there. We just saw the numbers and then you see like, okay, it's a 340 for one, 270 something for the other. So this one wins. But then once you arrive here and then you see how it really works and how the system is all or nothing per district and then per state, it's very interesting because to me, it looks very unfair from my point of view. In Spain, it's way more representative, even though there are big problems too. But basically, every candidate gets the percentage of votes that they had, and then you sum all these percentages, and the one that wins them is the one that gets elected. So it's a bit more of a fair system. It's still not one person, one vote, but it's much more fair than what I've been seeing here. And then it's something that fascinated me. And I started reading about it and I found it really, really interesting. And we tend to look up to the US and it's always been shown as the home of democracy and all these things that are said. But then when you look at the small print, then you start to find all the cracks in the system.
The Electoral College being the weirdest one. Yeah.
Yeah.
Yeah. Right. People from other countries don't understand. Wait a minute. Al Gore got more votes than George Bush. How did George Bush become president? It's like, well,
this is how it works.
That's how it works. And this happens every once in a while. And the thing is, it's happened more frequently lately. And
yeah,
this is sort of soon enough, because of demographic shifts, something like 15 of the states in the U.S. will have 2/3 of the population or something. So you'll have sort of this weird hollowing out where 35 states, which represent 70 senators, will only amount to a third of the population. People who like this sort of thing think divided government is good. People who don't want things to change, but it's starting to feel untenable. That land is getting so much of a vote.
Yeah.
That's like that. That's essentially, what it is. Land is getting a vote, and that's people should be getting the vote.
Mm-hmm. Yeah, well, maybe we can come back to this topic in 10 years and see if something changed.
Maybe.
I think
maybe.
I think it will take longer than that.
Yeah, I think so too.
Yeah, so that was really, really interesting, and I am very glad I had the chance to talk to you about this and bring you here to the show to take into account into all these topics that are on a daily basis on our lives. And we usually just read about them, but we don't think what's behind them and how they can relate to what we were saying at the beginning, this subject that was getting too hard for everyone at school. And suddenly when you leave school and you go to real life, you find out that you have to encounter it in almost everything you do and all the topics you discuss. So I was very glad to talk to you about it. I really thank you for coming to the show. And if you have a last remark, I'd be glad to include it here and to have you here again if there is a chance.
Yeah, well, thanks for having me, Pablo. It's interesting to be on the other side. Since I'm usually the one doing the interviewing, it's nice to be the interviewee for once, and it's nice to talk about math. I mean, I'm a mathematician for a reason. As we were talking before we started recording, my mom thought I should have been a physician, but I didn't want to be a physician. I want to be a mathematician. So here I am. I'm always happy to talk math in whatever context we can. So thanks for having me.
Yeah, that was great. And for our listeners, if you want to know more about Kevin Knudson, you can go to his website, kpknudson.com. And there he has a link to his blog, then also links to his podcast and his articles. And you can read more about what he's written and what he does. I think it's really interesting, and I'm really glad that we had you here. With that, I would like to say goodbye and then see you again next time. Thank you for listening. This episode of Culturico was produced by Pablo Sanchez. You can read our latest articles at culturico.com and Kevin's work at kpknudson.com. As always, we love your feedback. Feel free to leave us a review on the platform you use to listen to our podcast, or send us an email to podcast@culturico.com. And if you like our content, spread the word and let your colleagues know about us. See you next time!